Hi everyone. So this is it. This is the last topic in Unit 7, which for this year will be the end of the AP content. And this is about significance tests for two samples, but instead of being about two separate samples, they're about the difference in one sample. So we talked the other day about the fact that you know something is two samples if you have two separate samples, but you could also do a t-test for the difference if those two samples came from an experiment that was a matched pairs or a paired t-test, which is often what it's called. So in that situation, instead of using x bar 1 minus x bar 2, we use x bar difference, which is defined as 1 minus 2 or 2 minus 1. And instead of using the standard deviation of x bar 1 squared over n1 plus x bar sx bar 2 squared over n2, instead we use the standard deviation of the difference over the square root of n. So first things to realize is the sample size has to be the same for both, and they have to be kind of a before and after situation to help you. What's not going to change? Well, t's are still going to be around because we do not know the population standard deviation, and we're still going to do a statistic minus a parameter divided by the standard error of the statistic to find a t-value, and that t-value is then going to result in a p-value, and that p-value is what's going to allow you to determine if you reject or fail to reject. And you're still going to have a null hypothesis of mu equals mu sub difference equals 0, and then you're going to have an alternative hypothesis of mu sub difference is either not equal to 0 for a two-sided, mu sub difference is greater than 0, or mu sub difference is less than 0. Okay, so let's take a look at, we didn't as a group do the memory training test. Unfortunately, I just didn't quite get you there. But the memory training test is basically a strategy or a game where you give people different memory tests and compare their ability to remember the same information. And so for this particular situation, we have an experiment here. Suppose that 32 seniors were randomly selected to try both memory strategies. Each student calculated the difference in the number of words, strategy 2 minus strategy 1. The mean of the differences was x bar difference equals 1.5, and the standard deviation of the differences is s sub difference was 2.7. So this information is going to become my statistic information, right? So my x bar difference is 1.5, and my s sub x difference is 2.7. They are interested in a 0.05 significance level, and the parameter is mu sub difference is the average difference in the number of words remembered. Our null hypothesis is mu sub difference equals 0, and our alternative hypothesis is mu sub difference. Well, what do they want to know? Do the data provide convincing evidence that strategy 2 improves the memory? So if it improves the memory, then it would be greater than 0. We're going to name the procedure, and as I mentioned before, even though it's two samples, it's one set of data that was found by doing the same person in two different ways, and so we call it a paired t-test. Okay, and so then the next question is what are our conditions? Have they changed? Well, let's talk about this. So random they were randomly selected to participate. Okay. And because they were randomly selected, we also need to look at independence. Are 32 less than 10% of all seniors? Yes, we're good. And finally, is N greater than or equal to 30? And in this situation, 32 is greater than or equal to 30. So according to the central limit theorem, the sampling distribution would be approximately normal. And we don't have to worry about having the raw data here because we did have an N value that was large enough. Okay, so here we go. Well, my mean is 1.5. My standard deviation is 2.7 divided by the square root of N, which in our situation was 32, which gets me 0.477. So my general formula is so a t is a statistic minus a parameter over the standard error of the statistic. Draw my picture. This is 0. My standard deviation, negative 0.477, positive 0.477. 2 times that is negative 0.95 and positive 0.95. And 3 times that would put me out here at negative 1.43 and positive 1.43. Okay, and my difference is 1.5, which means we are way over here, and we are looking at what is this little tiny bit of probability over here going to be. Okay, and so when I do that, let's figure out what I'm going to get. So my value is going to be 1.5 minus 0 over 0.477, which is 3.14465. And based on what we've seen before we go looking, we're going to guesstimate that with a test statistic of 3.14465, even with 31 degrees of freedom, that p-value is going to be fairly small. So 32 degrees of freedom, well, remember we have to round down, so we're going to have 30 degrees of freedom. And we're going to have a 0.05 sigtail, right? And so we're looking for where is our value of 3.144 in relationship to this 1.69. And that value for us is somewhere over here. Oops, somewhere over here. And so that's going to correspond to a very, very, very small p-value. So let's say 0.0007. Okay. Does it have to be perfect? No. What you need to realize is how it's related. So according to my table, I got about 0.0007, which is less than alpha. And according to my calculator, we're going to be running a t-test here because it's the difference. And I'm going to put in my information under statistics. The mean is going to be 0. My x bar is 1.5. My s of x is 2.7. And my sample size is 32. And I want greater than 0. Which actually got me a value of 0.0018. So my calculator, 0.0018, which still is way less than 0.05. So how do we conclude this? Because 0.0018 is less than 0.05, we reject the null hypothesis. There is convincing evidence that the average difference, between method 1 and 2 is greater than 0.